Welcome everyone to another episode Data with Mick the Greek. And I hope you enjoyed my series until now, Load Big Data Efficiently. We learned a lot of things. What file formats are more efficient, how predicate pushdown is working, how the small file problem is behaving, and also what's the benefit of the schema. And today I just want to give you a summary in a nutshell, which things you should consider when you load big data efficiently or want to load big data efficiently. So if you missed the whole series, I'm gonna add up here a link so you can just go through all the details. And as always, if you want to see more videos like that and enjoy my channel, please don't forget to subscribe below. You're gonna find the red button. And with this, let's get started to the summary. So let's talk first of all about the file formats. So file formats can be structured into unstructured, semi-structured, and structured formats. So unstructured are very unorganized file formats like text or videos. And then we have JSON, CSV, and XML, which are rather semi-structured data. So it contains some text and some semantic, which brings some structure, but those things are not fully enforced. And then we have quite structured formats like Parquet and Avro, which are also capable for big data. And let me also go a little bit with my head away. Then for schema, type rules, they have a tabular format. They are splittable. They allow also binarized data like text or videos to be saved in a column. Also nested columns or JSON could be saved in a column Parquet, and the flexibility, the high compression with Snappy, and their structured enforcement of a schema, for instance, really brings a big value to the community for big data. And well, if we summarize a little bit, so CSV and JSON are both human readable, as we already mentioned. And those are row level formats, so data is saved on a row, not on a columnar basis. So if you want more details about that, check out the link above, which I'm going to link up. And they're all generally fast writes. So compression is possible, but not as fast as with Avro and Parquet, as they are really designed to be compressed and highly encoded. And CSV also has the issue that it's highly corruptible. So you probably know you can change the delimiter from a comma, for instance, to a space. And you can imagine if you have a string with a space, then it just screws up the CSV file. On the other hand, Parquet and Avro, especially Avro, is very efficient to save data. So if you want to just save big amounts of data, Avro is the file to go. If you want to have a very efficient loading, but also somehow a good writing, Parquet is a good format. And also there are statistics which are saved in Parquet, allows you to pull data quite efficient with predicate pushdown, which we're gonna see in a bit. They are compressible, but you should know that Avro and Parquet are not human readable, and also Avro has some limitations. Not everyone can read it, but Spark has a built-in option to read Avro. Looking into the results, so what did we do here? So I just took a 10 million row data set with 6 columns, and each of them had 8 files. So basically we're loading 8 files in parallel, let's say, with Spark. And in JSON, we can see this size is quite huge with 1208 megabytes. Then CSV is around half of it, and Parquet and Avro are significantly smaller. And similar with the write and the loading time. So as already mentioned, Avro is the fastest when writing. Loading time wise, Parquet is quite faster because Parquet is built on efficiency. And if you compare like JSON and Avro, for instance, you can see the size is 94% smaller, the write time and the loading time is smaller. And the same thing when you compare now CSV and Parquet. And I mean, why is it important to have a smaller size on a faster writing time? I mean, the topic is quite easy. You have storage costs, meaning less size, and we're talking about 94% means also less costs. And the same thing also for compute. So if you want to process data and your loading takes half of the time or even less, you save a lot of money, especially if you process a lot of data, terabytes, petabytes, at some point. So What we also saw is when you look a little bit into the Spark UI and the loading time. So basically, the loading time contains two parts. The first part is interfering the metadata, especially the schema. And the second part is the actual load. And what we saw and what's important to know is JSON doesn't contain a schema. So basically what Spark is doing, it creates a job to go through the whole JSON and interfere the schema. The same thing for CSV. So you have two options. Either interferes it based on the first row or it interferes it also through the whole CSV. I choose or show here the option, the second one where it goes through the whole CSV. And Parquet is saving the schema, but still Spark is loading those meta information out of Parquet. So also there we have a few milliseconds, but in JSON CSV, this part can be really substantial. And well, if you compare for CSV, 50% of the time also for JSON goes actually into this interference of the schema. Whereby for Parquet, for instance, is 30 milliseconds, and for Avro it's not really there because the schema is saved in the footer and loaded together with the data actually. Now we have a small file problem. So let's do and repeat the same experiment. But this time we have our 10 million row data set. And this time we split it once as a large portion, so 8 big files. And we have 100,000 small files, but the same size of the data. So the JSON is still 1.2 gigabytes big, for instance. So and what we see here is the total execution time for a small file, but also for the large one. And we can see in all the cases, the loading time is significantly slower and takes longer if you have a lot of small files. So JSON, for instance, 7.7 minutes instead of 6 seconds. And what we also see is that the meta part becomes significantly bigger. And the reason for that is that Spark has to load all those small files at once because a lot of files get into partition, and it's like an overhead for Spark. So what we have to know here, not faster, slower loading times and meta information, well, to get is significantly slower. And why this is, it's actually when we're looking into a Spark architecture. So we have a driver and we have multiple workers which are coordinated by this driver. And basically what the driver is doing, it assigns the small pieces of files to partitions. So if it's bigger bunches of files, it might split them into different partitions. If you have a lot of small files, it puts them all into a partition. And one partition is assigned to one task and executed at once. Meaning if you have a lot of small files in one partition, all those things like opening, closing the file, the schema interference, etc. has to be done by the driver all together at once. And I mean, if you're doing a lot of things in parallel, it's not very efficient. And all those metadata is also saved in the driver. So this brings also an overhead for the driver at the end. So except of the metadata saving and opening, closing the data, we also have this whole overhead of scheduling. So we have a lot of small pieces of data to schedule across the executors. And well, this reduces the parallelism and might also come to increase CPU cost due to a lot of serialization, deserialization. So you don't do one deserialization for a big file, but rather a lot of small files. And that's like also another overhead which we have. And I mean, the solving of the problem is quite obvious. So if possible, try to increase the file size, either by checking the source options or have an intermediate step where you just do load the data and save them again, just in bigger bunches. Well, and use file formats like Parquet or Avro, because we saw before that the issue regarding the loading time becomes way severe in JSON in JSON CSV than for Parquet and Avro. And well, and the other thing is you can reduce the metadata by defining the schema. And also the number of files per partition might be an issue. So we're gonna see in a bit that especially with openCostInBytes, a configuration Spark, you can just reduce the number of files per partition, and this might at least decrease the issue a little bit. So one topic we talked is the schema, like the force of the schema. So how do you define a schema? You have two options, either as a DDL schema or a Spark schema. And well, what you do at the end, in this case, here's an example for Parquet. You basically read the format Parquet and then use dot schema and then DDL schema or Spark schema to define it. I also gonna add here a link where you're gonna find a little bit more details about the whole schema topic. And well, when we now look at the topic with and without the schema, you can see that whenever we define the schema, the whole meta part is actually disappearing. So this job is not there anymore. And by that we really are able to reduce the loading time. So for instance, we had 7.7 minutes for JSON, and now suddenly we have only the actual loading time, which is the 80 seconds, so significantly decrease. And also the large file, when we're looking on it, even if you have large files, it's worth to define the schema, especially for CSV and JSON, because we have like a 50% decrease of a runtime. So for instance, you have 3 seconds, meta time just disappears. So we just have the actual loading time of 3 seconds. And even file formats like Parquet are having a decrease, like 0.4 seconds. So even the loading time, the actual loading time of the data becomes faster just by decreasing the schema, in this case by 33%. Of course, consider that the schema has also some danger. So if your schema in the file format changes and then you basically haven't defined this column in the schema, you might just ignore it. It's basically like dropping the column. That's like a little bit the danger. So you should be aware that the schema can also do a little bit of bad in your data. So that's something you should be careful. But if you're sure that the schema doesn't change or you're gonna be informed about schema changes, I would highly recommend to use this very efficient trick of loading data faster. And here we have also the percentages. So to just go through an example, so JSON without versus with schema for small files is 96% faster. And for bigger files, it's basically at least 50% faster. And well, small files versus large files is also a 99% difference. So JSON is 99% faster if you save them in bigger files than in small files. That's what it says here. And for Parquet, it's even worse. So here, basically, it's negligible how fast it is when you have bigger Parquet files. So now let's have a look on another option, how we can deal with smaller files. So we have something called openCostInBytes configuration. So with spark.conf and then Spark SQL files, openCostInBytes, you can set it. And this parameter defines something like a cost. So basically it says, what is my cost of loading one additional file? And I mean, you see the influence, especially if you have a lot of small files. So basically what it does is, let's have a partition which allows to be 128 megabytes big. So now you have like 4 files, 40 megabytes big. So you have 40 plus 40, that's 80. Then another 40, okay, also fits into it. So we have 120 megabytes, so it's below 128 megabytes. But what this openCost is doing to the second and third file, it adds a cost of having an additional file. So basically those 40 megabyte files become then virtually 44 megabytes. So it's 40 plus 44 plus 44. In this case, it's still 128, so it would fit into it. But now imagine that with very small files, which are bytes or kilobytes big. So if you wouldn't have this parameter, we would have added kilobytes of files up to 128 megabytes. Then we would have had like thousands of files in one partition, which would be create an overhead. But now we make the files pretty much, if it's bytes or kilobytes, it's pretty much around 4 megabytes big. And that means we are limiting it at, well, 128 divided by 4, it's 32. Around 32 files would come into one partition. And this means, well, per partition, per task, it's gonna be less scheduling and working for a driver and for our cluster. And well, it defaults to 4 megabytes, as you said, as you saw. And now what I did is I applied it for our small file experiment with 100,000 files and 100 million of rows for JSON Avro. And I mean, in this case, we are lucky that the default configuration is already quite efficient. But here you can see the difference. So what happens is if you have um, a higher open cost a bit, you see the performance becomes less because you have a lot of partitions which have maybe only two, well, in this case, maybe 10 files. And if you do, so this means like an overhead, a lot of overhead of scheduling, a lot of partitions, that's also bad. But then if you're going with the open cost low, we're gonna see, okay, we have a lot of small files in one partition, and this rather has like a metadata overhead of the driver to open and small and save the file and close the files and save the metadata and so on. So both directions are bad. Um, and in this case, usually you say you should avoid too many partitions. But in this case, it rather brings a benefit having more partitions to get rid of this metadata loading and opening overhead of the driver. Now let's talk about predicate and aggregate pushdown, especially with our favorite file format Parquet. So imagine you have a table. So name, female, and age are the columns. And now you want to get to know all the rows which have an age above 35. So that's how you write it in Spark. And what predicate pushdown is doing uh, is pretty much pushing this filter down to the source. So normally, for instance, with Python, you would load all the data and then do the filtering in the memory. So that's when you don't have predicate pushdown. But now we're gonna use statistics which are saved in your source in the database or in our Parquet format. We have statistics there. We're gonna see it in a little bit more detail, and only load the data relevant for us. So in this case, we are lucky that it even returned exactly the data which we only needed. So the filtering in memory is not needed anymore, and we can proceed with all further transformations. So of course, in reality, you might have like a data set with 100 million of rows, and then you want 5 rows out of it, but predicate pushdown at least gives a subset like 10,000 or 20,000 of rows. And then you already have a significant benefit because less data into memory means we have more memory available to process more data at once. And that means more efficiency. In short, predicate pushdown is an optimization technique filtering data at the source and often relies on statistics, and the benefits are clear, less I/O, less memory usage, and then at the end, faster queries. And those statistics are saved in the footer of the Parquet file. And so it's not only available for Parquet, it's also available for Avro, CSV, and JSON, just a little bit less efficient because it does some Spark magic in the background. It's available since Spark 3.10. So we talk about statistics in the Parquet file. So it's important to know how a Parquet file is actually constructed. So we have pretty much 3 levels. So we have a row group. So that's like the row level division, and it is defaulting to 128 megabytes. And that's a level where a file usually splittable. So if you have multiple partitions, one row group can go into one partition. Not half of a row group, not 1/3 of a row group, the minimum is one row group. And you're gonna realize, okay, the default parameter of maxPartitionBytes, which limiting the size of a partition, is also 128 megabytes. Then we have the columnar part, which relates to a columnar chunk within a row group. And then this columnar chunk is again divided into pages. So a columnar, I think a columnar, a page was around a few megabytes big always. And well, that's on the page level, the encoding and compression happen. So encoding means, for instance, if you have columnar, a string column, then the strings are mapped to a dictionary, to a digit number, which just saves a lot of size. So that's the easiest one. I also linked below in the slides a link for that, where you can find more details about the encoding strategies. So, and then the important thing is we have a footer, which is separated from the main data to be loaded separately and more efficient. And there we have metadata information. So on the file level, the number of rows, columns, the schema. On the row group, also the number of rows and columns. And on column level, we have things like min, max, null count, the distinct value count, the page indexes. And also page level in your versions, we also have min and max values. And those values can be really leveraged for the predicate pushdown, but also for something, but also for something called aggregate pushdown, which we're gonna see in the next slide. Here I'm just showing you an example when we're loading all the data. So when we load all the data, we're gonna need 16 seconds. If we do a column filter, so basically we just load part of the columns, we already can reduce the number of rows. And I did here now a row filter. To be honest, I don't remember which one we applied here, but probably ID smaller 300. And we can see that a row filter is not actually loading all the data anymore, even for JSON, but it just loads 300 rows. And that's like a big benefit if you define a row filter and don't load all the data. So in Parquet, as we talk about Parquet, we can see it a bit more interestingly. So if you load all that data, you have all the 10 million rows, which we have. But if you load on a row level filter, so that's like interesting on predicate pushdown, the base is not a row group, it's rather a page, and each page in this Parquet file was 200,000 rows. So even if we filter based on smaller 300, it gonna get us 200,000 rows, and then we do the filtering on the second step. But important here to see is that predicate pushdown is really loading less data into memory, either less columns or less rows. So and then we have something called aggregate pushdown. So the same thing as predicate pushdown, just for aggregations, like a count, like a min, like a max. And those are actually the three things which are currently supported. I think the support is quite limited and really works only for Parquet if you do those two configurations. So eliminate Parquet from this use v1 source list and activate predicate pushdown. And it only works on non-nested columns. And you need to do it on the whole file. So unfortunately, it will not push down aggregations if you just want the minimax from a row group or from an individual file in our Parquet folder, for instance. So also v2 seems to me unclear if it's more efficient or not. I saw like some slight efficiencies, but those were not always constant. So that's maybe something you can try out, but I'm not sure if it's gonna help for a lot of use cases. I hope they're gonna leverage those statistics in future soon, because you saw Parquet contains a lot of statistics and it will be easy to leverage them. So, and now let's come to the last topic. So we talked about our architecture. So we have the driver and we have the worker. And what we also said is normally we don't want too many partitions. And we want to, of course, use all our cores available. So, because what we said, our driver assigns partitions to a task, and each task is executed by a core. And well, what defines the number of partitions we are loading? So first of all, the number of cores. So by default, Spark tries to assign, which makes sense, to each core one partition. And also the number of Parquet files that are already mentioned. Parquet is splittable up to row group level for the partitioning. So if you have only one Parquet file with one row group, only one of your 4 cores gonna basically get something to do. If you have 4 row groups in a Parquet file, or you have 4 small Parquet files, all your 4 clusters gonna be doing something. That's something you can try by yourself. Theoretically, you can change the behavior of the number of cores, but I wouldn't recommend that. Then we have the max partition size. So this is limiting the size of a partition. That's a value we're gonna look today. So 128 usually works for big data because the row group size is 128 megabytes. But there are some scenarios if you have 5 files, for instance, or a lot of files which have some deviation in the size where you want to adjust it to get like a really good partition size. And then we have max cost per bytes, which is rather valuable, as we saw before, for smaller files. So what do we want to achieve, or what's a perfect distribution? So a perfect distribution is if we have now here, let's say 2 files with 4 row groups, that each core has time to work with a similar length. So we don't want that core 1 or core 2 is doing the work, we want it quite distributed. So that means something like that would be bad, because core 1 is doing significantly more work, and core 2, 3, and 4 are basically just sitting around. And so we're losing work which could have done with those cores. So that means we have some basic rules of good partitioning here. So first of all, we want a good parallelization. So usually people recommend factor 2 to 4 of your number of cores, exception of more smaller files. So if you have a few small files, like 4 megabyte files, you might be with a factor 1 also fine. As we saw before, if you have a lot of small files, like a small file problem, you might even want to go with the openCostInBytes parameter to a very high number of partitions. And the second thing is we want to have a uniform data set. So we want, in the best scenario, as we saw before, the partitions should be equally sized, and the number of partitions should be dividable by the number of cores. That's pretty much the 2 rules which I'm showing here. Then regarding the partition size, you should be care to not go too high. So the default is 128 megabytes, but recommendation I've seen is between 100 and 1 gigabyte. I wouldn't scratch the 1 gigabyte, and also it depends on which transformation at the end you're doing. So if you do very simple narrow transformations without any specialities and collects into the driver, then you are pretty much fine. But you should remember that it might lead to out-of-memory issues. And regarding distribution overhead, as already mentioned before, a high number of partitions can create a distribution overhead. So it's not necessarily always bad to have too many partitions, so factor 5, 6, but at some point you're gonna realize it's gonna be a big overhead, and usually you could see it in the Spark UI under your stages that, okay, the actual execution time is less than actually the execution time is less than 90%, yes. So basically you have scheduler overhead at sec and so on, which takes then over 10% of your actual execution time in your Spark job. Yeah, and as said, exception is a small file problem where distribution overhead is acceptable. So, and what's now important is that this parameter, max partition size, you can adjust it a little bit by, let's say, 10, 20%, rather higher than smaller usually, to get rid of empty partitions. So sometimes it happens that empty partitions are generated. Well, try to distribute a little bit your partition. It doesn't work always, but it can help in some situations. And another situation you also want to use it is when you have files which are gonna be exploded later on. So basically their size also explodes. So if you have a lot of nested columns, and then due to exploding into new columns, your size grows. So there you want rather to start with a smaller size to not get suddenly in the transformation process an out of memory issue. Well, and please check the video above. I gonna link to really have the details with a lot of experiments which we did here. So, and the last thing I want to say is, and that's just a sneak peek into one of my next series, Delta. So if you want to have it even more efficient and get rid of small file problems, etc., Delta is a tool to go. So two important features which are beneficial. The one thing is metadata, which is safe, which can be leveraged on a higher level on Parquet and is also leveraged better. So this might make even the actual loading, which we did with Parquet, faster. And the second thing is something like bin packing, meaning we have a small file problem and then you just have a command which basically puzzles your files to bigger batches and also structures your files in a way that you can leverage better predicate pushdown or file skipping which is needed. If you're curious, I have the link here below. Delta.io is the link to it. And yeah, with this, I want to give you a summary. So first of all, what's important is use big data formats like Parquet and Avro. If you really don't need a human readability, then use the schema whenever possible. So if you have some circumstances where columns might be filtered out, okay, that's a reason. But if you struggle with performance issues, especially with small files, the schema can save you significant loading time. Then, of course, avoid small files if possible. If not, reduce the overhead using the schema as mentioned, or check if the openCostInBytes parameter might also can assist you. Then let's apply column filter, row filter as close to the source so that our catalog optimizer can, well, leverage predicate pushdown and optionally also aggregate pushdown. Which gonna save you a lot of time. So if you're caching your data frame before applying that, that's a good example where it doesn't work. So the first thing, decide which rows and columns you need, and then do all the other fancy aggregations, joins, and other transformations. That's how you're gonna be most efficient. And well, and the last thing is use the conf. Okay, that's a typo. Sorry for that. Use the maxPartitions config to create a distributed partitions. And with this, thanks a lot for listening today. I hope you enjoyed the video. As always, please subscribe below to stay tuned for new videos like Delta, which are gonna start a series soon. And see you in the next episode. See you soon.